Video number 2. We may get a little rain. Let's continue with our discussion of chemistry and alchemy. Let's take a look at a chemical reaction in conventional terms. Here we have a funny sounding word. Stoichiometry. Okay, well, what the heck does that mean? Well, when I asked my teacher when I was 15, they said it's balancing chemical equations. Okay. Redox. What's that mean? Reduction, oxidation. Basically, fire. Now we have two chemicals here. We're going to combine potassium nitrate with sugar. There's a reason why I chose those two. First of all, they can be dangerous, but they're relatively safe in terms of they're not exceptionally fast, the flame temperature isn't too extreme. These chemicals were available to the ancients. They're both water soluble. So there's a lot of advantages for this to be somewhat of a beginner material. Now right here, you can see the chemical symbols for the molecules, the tiny, tiny particles of what each of these materials is made of. And the N is for nitrogen, and the O is for oxygen, C is for carbon, H is for hydrogen, and the O for oxygen again. Of course that all makes sense, but why is there a K there? It's called potassium, but yet there's a K there. That makes no sense to me. Perhaps alchemy will reveal some of the reasons why that is. Let's continue here with our math, and I've done the math for you, so we don't have to get too carried away with it. But when you combine these two ingredients at a ratio of 48 molecules of this one and 5 molecules of that one, combine it with the magic triangle here, which apparently in chemistry class means heat, a heat reaction. In engineering, the triangle is called delta, and it means change. So after the process, we get a change, and we're left with 24 parts of potassium carbonate, 36 parts of carbon dioxide, 55 parts of water, and 24 parts of nitrogen. So we're talking about molecular chunks here, and you can't count 48 molecules and 5 molecules of sugar. It's just extraordinarily tiny. So what you can do, though, is do the math of the molecular weights. Each one of these atoms has a specific weight on the periodic table of atoms. And once you go through it, you can get a pretty good idea of, by using the math here, which I don't want to really get into that much detail, but it ends up being 74% by weight of this chemical plus 26% by weight of sugar. Mix them together, and you're going to produce these ingredients that are the product ingredients. And they're in all different forms. Solids, potassium carbonate will be a dusty solid, probably of some kind. We're going to have gas produced, liquid water that might be hot enough to be a gas, and then nitrogen, which is a component of air. It's the breathless wind of air. Air is 90% or 80% nitrogen and 20% oxygen. Well, maybe the oxygen decreases with time as we burn it up if we're not smart about it, but you get the idea. So let's look at the alchemy and see if we can get some other ideas. So this is the symbol for saltpeter. That's the old name for potassium nitrate here. And this is the symbol for sugar. And there's your sugar right there. These powders, I crushed them up, the powdered sugar, powdered potassium nitrate. You can tell right off the bat that the potassium nitrate is like twice as heavy as the sugar. So on a microscopic level, this is what they would look like, the molecules. I sketched them out for you. Yeah. Okay. The saltpeter has this shape, approximately. And there's this double bond here with a nitrogen and an oxygen. Oh, by the way, it's beneficial if you've had some high school chemistry at this kind of a discussion. If you haven't, just hang in there. You'll pick it up eventually. So the potassium molecule or atom just floats around here. It's a loose bond. And this makes this chemical very reactive. The sugar here is a much bigger molecule, really sticks to your ribs, it does. And it is not to scale. This would be way bigger compared to this one. But I just sketched it up for you so you could have an idea what the tiny, tiny little parts look like. So let's look at the alchemical symbols and the equivalents. Here we have the word alchemy. Now, alchemy comes from two words, al and chem, K-H-E-M, originally. That's an Egyptian word. It means the black fertile sands, or the black fertile land. It's also, well, it just means the word black, so it could be the black arts if you want to look at it that way. But I prefer to think that it meant the black soil with which they extracted the minerals for their experiments. Now we got this other word here, stoicheion. Stoicheion is Greek, and it means element in English. Okay, well that explains this weird sounding word right here. So, metry is an English term for measurement of, the metric system, a measurement system. So stoichiometry is a measurement of the elements. Well, that makes sense. Oh, and here's this triangle symbol. Look at here. There's the triangle that we saw in chemistry class, and here's the triangle that we see in the alchemical symbols that we've got sketched up here. So these are the symbols that the alchemists would have considered to be elementary. Fire is an elementary principle. It's hot, it's dry, it's typically associated with the masculine energy form. Then you've got water. Water's life-giving. We tend to think of that as a feminine force, although I suppose male and female could possess both alike. Then you've got air, which is a gas, and you've got earth, which is a solid. So in a way, these are more like what we would call states. In modern chemistry, you would call these states. Gaseous, liquid, solid. But in alchemy, they have the states, but they assign the most common substance to that state. So for a state of energy, the most common thing you would observe is fire. There's different kinds of fire, different kinds of radiation. But in general, a common way of looking at it is fire. For a liquid, the most common liquid is water. It's sort of everywhere. It's the ingredient of life, as they say. And for a solid, well, you can't get much more solid than earth. It's got a lot of solid in it. And for a gas, air. It's everywhere. So you see, the old way was just a very broad brush of definitions. And what about this? Spirit. Well, we may not be able to get to that today, as we're getting a little bit of a rainstorm coming. But I think we'll use spirit in a sense that I'll take the rainstorm as a sign that I would mix the ingredients with water. After all, they are water soluble and they can always dry out later. So here's the symbols we're using. Saltpeter. Ah, that's the symbol. And look what it's called. Nitre of kalium. 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 How do you say that? Well, I don't know, but it explains the K in this symbol here. And in fact, kalium, or kalium, is the original name for potassium. Now, why would they call it that? Well, kalium comes from the word alkali. And alkali is two words again, alkali. And it means in the old, I believe it's either Latin or even Arabic, I think. It means that which is derived from the calcinated ashes. This, remnants of this campfire, this is kalium, alkali, alkaline. If you mix this with water, you get an alkaline substance. So that's where the word potassium and kalium get their origin. Now, why is it called potassium? Well, actually, this is potash. So the proper pronunciation would sound like Sean Connery, potassium, potash, So that's where you get the two different terms, and that's where the confusion in language comes from. And it's a pretty common ingredient. And so what I'm holding here is potash, kalium, and it contains potassium carbonate, among other things. But a large percent of it is potassium carbonate. And apparently, when our reaction is complete, we'll be producing some of this, as would be expected from many fire-type reactions. If we take a quick look at our, I guess you could say, pretend alchemical mix here. Saltpeter, sugar, plus fire gives double fire, plus 3 of the other elements. Well, that's kind of what we got here. We don't know what these elements are. Maybe we can build an apparatus to capture them and test them and figure it out. Now, modern chemistry, of course, predicts what they will be. So for our next video, since it's going to rain, I'll take that as a sign. I'm going to mix these two ingredients together. They're both water soluble. Well, heck, let's just do that right now. Let the rain put a little water into them. You can see how they look. There's the saltpeter. Oh, we got a little... Definitely don't let any bugs get in there. That would be a living creature, and that would throw off your whole chewy. Would mess it up, unless you were trying to, and then that's a whole nother deal. We don't need to get into that today. Well, you can hear that thunder coming. I'll take that as a symbol of us mixing this with water. There's the sugar, a little different color. Sugar's a little bit lighter. Saltpeter. Really, a hygroscopic material does not want to come out of the container. It picks up moisture from the atmosphere. So what we're going to do, we'll just mix these all around. Nothing fancy. We'll add a little water to it whenever it rains. Get a little rainwater. Mix it in there. Let it mix together intimately with the water and then dry out. And then we'll continue with our next video. And on the next video, we'll have a little action. And I'll show you what I think the circle means, the spirit circle.